So these last days, we have been discussing, the consequences of an action principle, right? We defined something that was the action. The action was the integral over time of the Lagrangian. And from the stationarity principle on this action, we derived the Euler-Lagrange equations. Also from the Lagrangian, we constructed the Hamiltonian as a Legendre transform. And, we also wrote down the Hamilton's equations that follow from this function, the Hamiltonian, okay? And we showed that the Euler-Lagrange equations and Hamilton's equations are completely equivalent. So now a natural question to ask is there an action principle that directly leads to Hamilton's equations? Is there a stationarity principle equivalent to the one that we already discussed for the Lagrangian, but now for the Hamiltonian that leads to Hamilton's equations? And the answer is yes. And so because this other approach is going to be useful for other things, I think it's interesting that we discuss it at this point. Okay, so this goes by the name of modified Hamilton's principle. Remember that the action principle that we discussed in terms of the Lagrangian is also called Hamilton's principle. So now we're going to talk about the modified Hamilton's principle, which is another way of saying that we want Hamilton's equations derived from an action principle, Okay, so let's start with the action. The action was the integral over time from t1 to t2 of the Lagrangian. This is going to be a function of q of t, q dot of t, and maybe also t. For all the generalized coordinates that we have in our problem, I don't bother about how many of those we have. But now we write this Lagrangian in another way. We just write dt from t1 to t2, and we rewrite the Lagrangian in terms of a Hamiltonian. So that's going to be the sum from j equals 1 up to n. Now I do have to, identify how many of these coordinates I have. I have little n of them, minus the Hamiltonian. It's a function of qj, pj, and t. Right? The Lagrangian can also be written in this fashion, okay? With p's and q dots and everything. Now, this thing here is a new object. I mean, it is the Lagrangian, but remember that the Lagrangian is not only a function, but it's a function that depends on certain variables, depends on q and q dot, okay? Whereas the expression that we have here is a mixture, has, q's, q dots, p's, everything, right? So this is a new object. It's not strictly speaking, this object here is not the Lagrangian, and strictly speaking, is something new because it depends, as I'm saying, on q's, q dots, and p's, okay? So this modified Hamilton's principle takes this object here as a function f of the following variables: qj, q dot j, pj, p dot j, and t. So it's fully democratic. Now we have everything. We have q, q dot, p, and p dot, all of them, okay? And we're going to treat all these variables, qj, q dot j, pj, and p dot j, as independent. Okay, so this is what we mean when we write a function of we just, list here all the variables in here are independent of each other. So we're going to take this expression in parentheses here as an expression of the variables q dot, p, and p dot as completely independent. And now we're going to play this game. Now we just do the usual variations, right? So q of t and alpha is going to be qj of t and 0 plus alpha times an arbitrary function, eta j of t. Okay, and the same for the p's. P of t and alpha is going to be pj of t and 0 plus alpha times another function, because the q's and the p's have nothing to do with one another, eta j of t. Okay, so that means that the variations of the qj's are given by this parameter alpha, eta j, and the variations of the pj's are given by this parameter alpha and the eta bars, okay, of j. And there have to be boundary conditions, and the boundary conditions will be the same as the ones that we took when we were, dealing only with the q's, right? So this is going to be like eta j of t1 or t2 is going to be 0, and eta j bar of t1 or t2 is also going to be 0. So we have a situation in which, right, we move in the q space from t1 to t2, right, and we take variations in q's and in p's, right, in this multidimensional space. Okay, we just take all these variations. Exactly as we did, in the previous case, where we only had the q's as the variables. All right, so now the action principle, the stationarity of S becomes the condition delta S equals 0 under all these variations, right? Now we vary the q's and the p's as if there were, independent variables. Okay, so that means that delta S, which is going to be 0, is going to be the integral over t from t1 to t2 of delta f, my function f, of q dot, p dot, and t. Okay, and so therefore this is the same as the integral dt 1 to t2 sum over all the variables from 1 to n of derivative of f respect to qj delta qj plus derivative of f respect to q dot j delta q dot j. That was already the same as, when we only had q's as the variables, but now we also have the p's, right? So the derivative of f respect to pj delta pj plus derivative of f with respect to p dot j delta p dot j. All right, so that's the thing. Okay, and now we're going to manipulate. Well, we have to identify all these variations and use integration by parts. So the strategy is the same as what we did when we were dealing with the standard action principle. Okay, so this is what we remember here. We just remember that the derivative of f with respect to q dot j delta q dot j is the derivative of f with respect to q dot j, and this is the derivative of q with respect to t, right? The variation of the derivative of q with respect to t. That's what q dot is, right? But this delta here is the variation with respect to alpha, and alpha does not depend on time. So that means that I can commute these two derivatives and write this as the derivative with respect to time of delta Q, right? And now this I can always write as the derivative with respect to time of the whole thing minus the derivative with respect to time of the derivative of f with respect to q dot, whole thing times delta q. This is a dot. Huh? Let me just make it clear that here I have a dot. Okay? And this I'm going to do also. So same thing for pj's. Okay? And this I'm going to use in these integrals here. So I'm going to use it here for delta q dot and here for delta p dot. And you recognize that essentially what I'm doing is integrating by parts, right? So 0 is delta s equals integral dt from t1 to t2, sum j equals 1 up to n of, and now I have derivative of f with respect to qj times delta qj. This I already had, but now I have this extra piece that comes from the integration by parts. So I have to put it here, minus d dt, derivative of f with respect to q dot j. Okay, this is what I get for the q's, plus derivative of f with respect to pj times delta pj. But now I also have the same thing coming from the integration by parts, minus derivative with respect to t partial of f with respect to p dot j. Okay, this is that. But of course, since I integrated by parts, and I have now total derivative of all these terms, right? So this I'm going to add plus integral dt from t1 to t2 of the total derivative of the sum from j equals 1 up to n, derivative of f with respect to q dot j, delta q dot j, plus derivative of f with respect to p dot j. Oops, here there should be a delta p dot j, a delta pj, and that's it. Okay, so this is just this integration by parts, and now is the usual thing, right? Remember that delta qj at t1 or t2 is 0, and delta pj at t1 or t2 is also 0 because of the boundary conditions that we had before. Okay, right? The boundary conditions, these two boundary conditions for eta and for eta bar. So with these boundary conditions, that means that this whole term here, because it's a total derivative, is going to be the thing inside the square brackets evaluated at t2 minus the thing inside the square brackets evaluated at t1. But all the deltas cancel, both at t1 and t2, so this whole thing vanishes. This term here is 0, okay? That's the usual argument we used before for the q's, but now we use it for the q's and the p's because they play exactly the same role, okay? So that means that 0, which is this delta s, is actually the integral from t1 to t2 of the sum from j equals 1 up to n of the first term only, which is, I'm going to write it, partial of f with respect to qj minus derivative with respect to t of partial of f with respect to q dot j times delta qj plus derivative of f with respect to pj minus d dt derivative of f with respect to p dot j delta pj. Okay. And this is integrated over t, of course. Okay, so now the condition that this has to be 0, since delta qj, delta pj are independent of each other, means that instead of all this sum integrated equals 0, what I have is that each and every one of the terms has to be 0. So that means that the derivative of f with respect to qj minus d dt, derivative of f with respect to q dot j has to be 0, and derivative of f with respect to pj minus d dt, derivative of f with respect to p, oops, let me put a p dot j has to be 0. So these now become the equations of motion. So this and these are the equations of motion. Equations of motion. Okay? Now, let us see what these equations of motion are, right? So now we have to check that from this principle that we just derived, okay, we do get the Hamilton's equations, right? And this, of course, this is for j from 1 up to n, for all the variables, all the generalized coordinates that you have, all the variables that you have. So now we're going to apply these equations, right? We're going to apply them to our function f, but our function f, function of q dot, pp dot, and t, was nothing but the sum from j equals 1 up to n of pj q dot j minus the Hamiltonian function of qj, pj, and t. So we have to apply it to this, okay? So let's start one by one. So what does the equation partial of f with respect to qj minus d dt partial of f with respect to q dot j equals 0 tells us? What does this equation tell us? So let's compute. So what is the derivative of f with respect to q? Derivative of f with respect to q, j, is p q dot q, and again p, they are all independent of each other. So when I take the derivative of this f with respect to q, here I don't see any q, here I do see a q. So that's minus the derivative of h with respect to qj, right? So that's this part. And what is the derivative of f with respect to q dot j? Well, so here I see a q dot. So when I take the derivative of f with respect to q dot j, I pick up pj. And then h does not depend on q dot. It depends on q, depends on p, and also on t, but it does not depend on q dot. So then this is p, okay? So what this equation says is that minus derivative of h with respect to qj minus, so let me pull this derivative on the right-hand side. So it's going to be equal to the derivative with respect to time of p. So that is p dot. Aha, so that's Hamilton's equation. That's one of Hamilton's equations, right? So that's one of Hamilton's equations. Good. So now let us do the same thing now for the p's, right? So that's partial of f with respect to pj minus d dt partial of f with respect to p dot j equals 0. All right, so that leads to, who is partial of f with respect to pj? So f is here again. So we just take the derivative with respect to p. Here I have a p, and inside the Hamiltonian, I also have a p. So when I take the derivative of f with respect to p, I get q dot j, yeah, minus the derivative of h with respect to p, j. That's what I get. And now, what is the derivative of f with respect to p dot j? Okay, but I look, and inside f, there is no p dot, so that is 0 directly, right? There is no p dot anywhere. So that means that this has to be 0, which is the same as saying that q dot j has to be partial of h with respect to pj. Aha, so that's the second Hamilton's equation. So that those two indeed are Hamilton's equations. Okay? So this principle does lead to Hamilton's equations. And well, that's a curiosity if you wish, but you will see in a few days that this principle is going to be useful as well when we start discussing what people call canonical transformations. All right? Okay, so now we're going to change subject. So before we do that, any questions or comments? Hello, you guys are still there?
All clear.
Okay. So no questions or comments?
No.
Okay. All right, good. So let's move on. So now we're going to start discussing one of the aspects that are, most important in the context of theoretical mechanics, or in the context of Lagrangian and Hamiltonian physics, right? Which is symmetries and conservation laws. Symmetries and conservation laws. And so this is going to be the first time that we're going to see a version of Noether's theorem, which is the theorem which controls the connection between symmetries and conservation laws. Okay, so there is going to be one example of Noether's theorem now, and there will be another example of Noether's theorem when we will discuss fields instead of, discrete variables qi, functions of space and time, fields, right? So why do we care so much about conservation laws? Well, we care about conservation laws because they make our life simple, right? They make our life simple. We know that using the fact that energy is conserved or angular momentum is conserved, etc., simplifies our life, right? Makes the solution of the equations of motion simpler, okay? And we also know, so that's why we care about these quantities. And if there are other quantities which are conserved, so that's even better, okay? So we don't care particularly about energy and angular momentum, okay, unless they are conserved. If they are not conserved, for a system that doesn't conserve energy makes energy less interesting, right? And we also know, or we also suspect, if you wish, that this is related to asymmetry of some kind. Why? Because we know, example, that if the Lagrangian, which in principle is going to be a function of q dot and t, right? If the Lagrangian, for some reason, does not depend on q, if L does not depend on q, on a certain qj, okay, then since the derivative with respect to t of the derivative of the Lagrangian with respect to that q dot j has to be the derivative of L with respect to qj, and this is 0, It means that the derivative of L with respect to Q dot J, which is nothing but Pj, is constant. Right? So that already tells you that here we have a certain constant of motion is conserved. Pj is constant, along the trajectory of the motion. So that means that it is conserved, is constant, or is conserved, right? It's the same. And this happens as a consequence of the fact that the Lagrangian does not depend on Q. So here the symmetry is Q goes to Q plus constant, plus anything. Let's say A, a constant. Oops, A. Right? For that particular J. So L does not depend on Q. So if I shift Q by a constant A a number, the Lagrangian remains the same. So we suspect that there must be a symmetry. Okay, another example that we have already seen is that if the Lagrangian, which in principle depends on Q dot, and T, if does not depend on T, then the derivative of L with respect to T explicitly is 0. And we know that the derivative of the Hamiltonian with respect to T, the total derivative, equals minus the derivative of the Lagrangian with respect to T explicitly. And this is now 0. So this means that H is conserved, or a constant. It's the same. And again, the symmetry is very similar to the previous one, is symmetry under the shift T goes to T plus A, where A is a number. So it's again some sort of translation, right? It's translation in time, and here is translation in the coordinate Q. All right. So all these examples in which we see that the Lagrangian, the system does not depend on a certain variable, Q, okay? We say that Qj is cyclic. We say Qj is cyclic, is a cyclic variable, okay? Here we could also say that T is cyclic, but that's not what people say. I mean, this word cyclic, the adjective cyclic, is reserved only for the generalized coordinates, not for time. Okay, so we do see all these examples. So now we are in a position to formulate the general situation that is going to lead to Noether's theorem. Okay. So let's define a symmetry transformation. First, we have to define what we mean by a transformation, and then a symmetry transformation. Okay. So transformation. First, transformation. Okay, what is a transformation? Well, a transformation, let's call it T, is essentially a change of variables. So we go from Q given by Q1, Q2, up to Qn and T, and we transform it, we change them into Q prime, which in general is going to be a function of all the Qs and also time, and T prime, which is going to be also a function of all the Qs and time. So we make a general change of variables. We just mix them all together, but we're only going to consider infinitesimal changes. So the Q prime is going to be the old Q plus a small contribution, which is going to be a function of Q and T, okay? So it is, Q prime is a function of Q and T, but it's a function which is very, very close to the old Q by an amount delta Q. And here the same thing for t. So t is also going to be t plus delta t, which is a function of the all q's and t's. And this delta q and delta t, infinitesimal. That means small, but not zero. In other words, delta q is going to be an epsilon, delta t is going to be an epsilon, and epsilon is much smaller than 1. And we are only going to consider changes to first order in this epsilon, to first order in this delta q. Okay? Now, the consequence of that, I can say that q prime is a function of q, or I can also invert that and say that q is a function of q prime. This is clear, right? So that means that if I start from the action S, remember, there was a functional of q of t and t given by the usual integral over t of the Lagrangian. I don't write it, okay? That means that this is going to be the action of the q's now are a function of q primes and t primes. T is a function of q prime and t prime by inverting this, okay? The q is a function of q prime and t prime, and t is a function of t prime, q prime and t prime by inverting this. So I replace them in here. So this, in general, is going to be a new action of q prime and t prime. I just make a change of variables, right? So therefore, the function is not going to, the functional in this case is not going to be the same. In principle, this S prime is going to be different from S, right? But this is the substitution rule. I just change variables, and this is what I have to do. Okay, so 2. T now is a symmetry transformation. Right? So far, T was a transformation, and now is a symmetry transformation if S prime equals S. Let me put a beautiful prime in here. If S prime equals S, so if you wish, let me just put all the dependencies, Q prime, T prime, T prime. The functional dependence is the same. So the form of the action does not change, okay? Now, it may be that the action does not change even though I have changed the variables because the Lagrangian doesn't change, or because the Lagrangian does change, but it does change in a way that the integral over time, which defines the action, does not see the difference, okay? And this is something we will have to take into account at some point. All right, so this is a symmetry transformation, and now we have to see what consequences we can derive from this condition, right here. Okay, any questions? I heard a little noise, so any questions, or the situation is clear and I can carry on?
No questions.
Okay, so now, if I take S of Q prime, T prime, T prime, minus S of Q, T, T, I'm going to get 0, right? This guy here is the same as S prime because of the condition number 2. And the condition number 1 tells me that S prime evaluated at the prime variables is the same as S evaluated at the unprime variables. So therefore, this is 0. So I'm going to compute now this 0 in a very complicated way. That's the condition that I have. for a symmetry transformation. All right? So now, I have to write first. So this is, if you wish, I can make it explicit. So now I have to write, you know, the expression for the action after I make the transformation. Well, it's S prime of the prime variable. So therefore, this is integral dt prime from t prime 1 to t prime 2 of L. In principle, there will be a new Lagrangian, L prime of Q prime, Q dot prime, and T prime, right? Everything primed as here, minus S. So minus the integral dt from T1 to T2 of the Lagrangian as a function of the unprimed variables, Q and T. Okay? Now, so this expression here in this difference, I'm using the general expression for the S prime action as a function of the prime variables, and here the general expression for the action in terms of the unprime variables. But now I have to impose that the action S prime is the same as the action S. So that means that this L prime here cannot be anything. It has to be something special so that this integral gives me the same as S, right? And now, what is the condition on L prime function of Q prime, Q dot prime, and T prime to give me the same action S as given by the Lagrangian L? So what condition do I have on this L prime so that this is true, so that the action is the same? I mean, one possibility is that L prime equals L. This is obvious, right? So if L prime equals L, then this is going to be true for sure, right? If L prime equals L, then the integral of L is going to give me the same as S in the new variables, right? So this is true. But is this the most general condition?
If we add to any of side of this equality, like full derivative over time of some function, it will be still true.
Right. So we can add, so this is not the most general condition. We can add a time derivative of a function, okay? Of a function, what kind of function? Let's call it G. Can it be a function of anything?
I mean, for sure, it can be function of time, but
Can be a function of time, yes. Could it be a function of Q dot and Q?
I don't know. But
We already discussed this thing, huh? What is the most general change I can make to a Lagrangian that does not change the action?
It can depend on the Q's, but not on the Q dots.
Exactly. Very good. So Q. Okay. And since the variables here are prime, prime, and prime. Right. But not the Q dots. Remember, not the Q dots. The reason is because the Q's are the ones that vanish at the boundary condition, at T1 and at T2. The variation of the Q's, you know, has to vanish at T1 and at T2. But there is no condition on the variation of the Q dots, right? So that's why this function can only depend on Q's and also on time. All right, good. Now, so that is going to be a function like this. But now, remember, you know, this change from L to L prime happens as a consequence of this change of variables, these delta q's and delta t's that we have here. And these variations are infinitesimally small, okay? So that means that this function here is also infinitesimally small because it comes as a consequence of this change of variables, right? If I didn't make any change of variables, this delta g would not be here. The Lagrangian would be exactly the same. Nothing would change. So if there is a delta g here, it has to be of first order in the epsilon that we had before, because it comes out as a consequence of the change of variables. All right? Do you all agree with this?
Yes.
Okay. So that means that now our 0 equals the 0 that we had before, the difference between the integral of t prime L prime minus the integral over t of L equals the integral over t prime of t1 to t2 of L prime, but now this is L of q prime, q dot prime, and t prime, plus derivative with respect to t, in fact, prime of delta g of q prime and t prime. Okay, so that's the first term. And then the second term, minus the integral dt from t1 to t2 of the Lagrangian of q dot, and t. Okay, good. All right, now 0 equals, okay? And so let's, first treat this term. So this is t prime 1 and t prime 2. Did I put primes here? Yes. Okay, good. So this is from t prime prime to t prime 2 dt prime. Okay, so t prime 1 to t prime 2 dt prime. Now I just I have to write down everything in terms of the same variables. Now I'm going to undo the change of variables and write the primes in terms of the q's and t prime in terms of t, okay? Remember that the transformation that we have is this one. So it's q prime equals q plus delta q, and t prime equals t plus delta. And this is a function of q and t. This is a function of q and t. So this is the change of variables, the transformation that I'm making, okay? So this is dt prime dt times dt. So now I can, let me write it a little better. So this is dt prime dt, right? This is the transformation of the Jacobian. So that means that now I'm integrating over t. Here I have the Jacobian, and now I have to rewrite all this, okay? So let's rewrite the first term. So that's going to be L of q prime, which is q plus delta q, q dot plus delta q dot, okay? And then t plus delta t. So that is the change of variables of the first term. Now it comes the one with the delta g, right? So that's again integral dt from t1 to t2. Now the Jacobian dt prime dt. And the derivative with respect to t prime, delta g of q prime, t prime. Okay? And then minus the integral over t, t1 to t2 of the Lagrangian of q dot, and t. Good. Okay. What is this Jacobian? Well, the Jacobian dt prime with respect to dt is dt prime with respect to dt is 1 plus the derivative with respect to t of delta t. Right? If I take the t prime equals t plus delta t, the derivative of t prime is precisely this. Okay? And this times the Lagrangian. So that's going to be the Lagrangian. I'm going to write it. I'm going to leave it as it is. So this I'm not going to change. Okay? But here I also use that this is 1 plus the derivative with respect to t of delta t. Good. Okay, so this means that 0 equals integral dt from t1 to t2. I pick first the 1, so that's L of q plus delta q, q dot plus delta q dot, and t plus delta t. Now I pick the other term with the derivative, so that's the integral dt from t1 to t2 of derivative with respect to time of this function delta t times the Lagrangian. And now notice one thing, because here the delta t is already a further epsilon, is already a further 1 in the Lagrangian, which in principle depends on q plus delta q, q dot plus delta q dot. I can immediately put q dot and t, because if I put also the delta q's and delta q dots and delta t's, that would be a second order, right? This is already a first order, so I can take this guy, at lowest order. I don't have to take into account the variations in q dots, and t for this term when I multiply it by delta t, the derivative of delta t actually. Okay, so that's one thing. Okay, now plus. Here, something similar happens, right? Here, this guy here, again, is a further epsilon. Remember, is an infinitesimal variation, is a further epsilon. And the delta G is also a further epsilon because it appears as a consequence of the transformation, right? This we already argued before, that this was a consequence of the transformation. So this is a further epsilon. This is also a further epsilon. So that means that I can forget about this delta t when it multiplies the delta g, and I can pick only the 1. So that's going to be integral dt from t1 to t2 of the derivative with respect to t prime of delta g of q prime and t prime. Okay? But even more, since the delta g is a further epsilon, because it appears just because I made an order epsilon change, this guy is a further epsilon, I can, what is said, with impunity, I can for free come and replace prime variables here by unprime variables, because the difference between prime and unprime is also further epsilon, and delta g was already a further epsilon, so the difference will be a further epsilon squared. So I can forget about the primes in here altogether. Okay? And then I still have the last piece. So minus integral dt from t1 to t2 of the Lagrangian L of q dot, and t. Okay. Now, any questions at this point? You guys agree with all these manipulations so far?
Yes.
That was a question, yes or no?
No, no question.
No.
No, okay. So questions. Where do you guys disagree? Do you guys disagree or not?
No.
Ah, so you guys agree. I thought you guys were in disagreement. So you guys agree. So with all the manipulation that this, so far, this is the right expression to first order in delta Q delta T. In other words, to first order in epsilon. I still have to expand this term. Huh? This term here, I still have to work with it a little bit. I'm going to do it now. But to first order in epsilon, this is true. Agreed?
Well, I think that's an integral missing of G.
There is a term missing?
Yeah.
Where?
From the term of delta G.
Yes, here. This one?
1 plus the derivative of delta T. And then down, you just put the part of the derivative, but not the 1.
No, but look, and this term here, so you are complaining about this term, right?
No, the other one. The one multiplying the 1.
No, but this 1 times derivative of delta G is what I wrote here.
Okay, okay.
You see what I'm saying?
Yes, yes.
Okay, so this, let me just put it like this. I mean, this derivative of this dt prime dt is the 1 plus something. And what I'm keeping is the 1 times the derivative of delta G.
Okay, okay, thank you.
All right. Any other complaint or comment?
No.
So you guys are in agreement so far?
Yes.
Okay, good. So now I'm going to expand this Lagrangian L, using the delta Q dot, and delta T are small. Okay, so that means 0 equals, of course, 0 equals, of course, the lowest order term is going to be L of Q dot, and T. So that's integral dt from T1 to T2, L of Q dot, and T. And now it comes all the variations due to delta Q dot, etc. So that's going to be plus integral dt from T1 to T2 of derivative of L with respect to Q, delta Q, plus derivative of L with respect to Q dot, delta Q dot, plus derivative of L with respect to T, delta T, right? Minus the integral, minus the integral dt from T1 to T2 of the Lagrangian, Q dot, and T, this guy is this guy, okay? And then the other two terms, plus integral from T1 to T2, delta T, derivative respect to time, delta T, times L of Q dot, and T, plus integral from T1 to T2, delta T, of the derivative respect to time of delta G, function of Q and T. Okay, so in the next slide, I'm going to write it a little bigger. Okay, the only thing that now you guys have to see is that this term cancels that term, obviously, because to first order, that would be no change. So the first order has to cancel. And you have to have only, we're taking a difference, right? So you have to have something which, it's only of first order. And here you see it. Delta Q dot, delta T, and delta G. Okay, so 0 equals, all right, integral delta T from T1 to T2, and I collect all the terms. Derivative of L respect to Q, delta Q, plus derivative of L respect to Q dot, delta Q dot, plus derivative of L respect to T, delta T, plus L derivative with respect to t of delta t, right? And then the g plus the derivative with respect to t of delta g, right? And this has to be 0, okay? Good. If this has to be 0, it has to be 0 identically, that means for any t1 and t2, then that means that the integrand has to be 0, right? Remember that this was an identity. It happened regardless of t1 and t2. It was just that the actions were exactly the same, right? So we were computing an identical 0 in a very complicated way. So that means that the integrand now has to be 0. So that means that dl dq delta q plus dl dq dot delta q dot plus dl dt delta t plus L derivative with respect to time of this variation of the time variable plus the derivative with respect to time of the delta g has to be 0, okay? All this has to happen, okay? And this has to be, right, the condition star has to be satisfied identically. That is to say, without the equations of motion. For T to be a symmetry. Remember that we had this change of variables, this transformation, and we required that T had to be a symmetry. And the consequence is that this has to be 0. And we have not used the equations of motion at all. So this has to be a property of the action, or if you wish, a property of the Lagrangian. The Lagrangian has to be such that when I make these transformations, nothing changes, right? The action doesn't change. No, it's not nothing changes, but the action, which is the thing that we're looking at, does not change. And we have not used the equations of motion, okay? So this condition is what is called a symmetry test. Is what is called a symmetry test. Okay, is what is called a symmetry test. That means if this is true, T is a symmetry. If this is not true, T is not a symmetry, without using the equations of motion. Okay. Now, when we're going to look at certain examples, okay, and then we will recognize what this symmetry test is. Like, for instance, we're going to see that whenever, you know, all the moment of all the forces vanishes, then the angular momentum is conserved, right? Here there is no conservation yet, okay? But we're going to see that this symmetry test is going to be, for example, the condition that the sum of the moment of all the forces is 0, okay? And then we will see that the conservation is that the angular momentum is conserved. Okay, so we'll see examples of this symmetry test. What we see so far is that for T to be a symmetry, this condition has to be satisfied, you know, without using the equations of motion. Without using the equations of motion, sometimes it's called off-shell, okay, off-shell. So I'm not going to use this nomenclature, but I just let you know, because some books talk about, you know, the equations are satisfied off shell or on shell. On shell would be using the equations of motion, okay? So this has to be satisfied without using the equations of motion, so therefore off shell. Okay, now we're going to see the consequence.
Sorry, can you tell me what is the underlying word here?
Underline, what do you mean?
You underline the word like e.g. and there is some word there which I cannot read.
Oh, without, it's I, E, and this is without. So I, E, without.
Okay.
Without the equations of motion.
Okay, I understand now. Okay, thank you very much.
Sure. Okay. Any other question?
No.
All right. So consequence of this symmetry transformation T. Now we're going to use the equations of motion, okay? But that will require a few manipulations. Okay, first, remark the following, okay? We're going to have to deal with the variation of Q dot, okay? So that requires that we compute this thing, okay? So let's first compute Q dot prime as a function of T prime. This is the derivative with respect to T prime of Q prime as a function of T prime, obviously. And this is the derivative with respect to T prime of, who is Q prime? Is Q plus delta Q, function of T, right? Okay, now I change variables from T prime to T. So that means it's the derivative with respect to T of Q plus delta Q. And now the derivative of T with respect to T prime. Okay? Now, who is the derivative of T with respect to T prime? You just go back. And here it is. You take the derivative of T with respect to T prime, right? So you take the derivative of T with respect to T prime, and this is nothing but 1 divided by 1 plus the derivative with respect to T of delta T. That's exactly what it is, okay? But since this is already of order epsilon, I can expand. So this is going to be derivative with respect to T of Q plus delta Q. And now this guy is 1 minus derivative with respect to T of delta T, okay? Plus dot, dot, dot. But I forget about the dot, dot, dots. So if you wish, I can approximate this thing like this, plus higher order, okay? And here I still have to keep, the expansion to first order invariations. So that means the derivative of Q respect to time, that is Q dot, okay? And then the derivative respect to time of delta Q. All right, and this whole thing multiplied by 1 minus the derivative respect to T of delta T, if you wish, plus order delta T squared, or order epsilon squared in general. Order epsilon squared here, and also here. I'm going to put it here, plus order epsilon squared. All right, so now we multiply these two terms, okay, to first order. So that means that I have Q dot, then this is Q dot, plus the derivative, derivative with respect to time of delta Q, minus Q dot, derivative with respect to time of delta T, plus order epsilon squared. You agree? That's expansion to first order in the variation epsilon, okay? So now I compare Q prime T prime dot with Q dot, okay? So I write it again. So that I have q prime dot t prime, that is q dot plus derivative with respect to time of delta q minus q dot derivative with respect to time of delta t plus order epsilon squared. That's what I obtained. So that means that the variation of q dot, which is what I have to compute because I have all these variations in the symmetry condition, in the symmetry test and all that, is the difference between these two. So this is d dt delta q minus q dot derivative with respect to time of delta t, okay? Plus order epsilon squared, which I'm going to forget because the calculation that we are doing here is of order to first order in epsilon, okay? So that's delta q dot. And this we're going to know it. We're going to use it. We're going to use this expression now, all right? So now, let's go back to our 0 equals delta s condition, right? So we have 0 equals delta s equals, and now we had, remember, the integral from t1 to t2 dt of derivative of L with respect to q delta q plus derivative of L with respect to q dot delta q dot plus derivative of L with respect to t delta t, right? Plus L derivative with respect to t of delta t plus the derivative with respect to t of delta g. That was the condition we had when we, before we said this has to be 0, you know, identically as a symmetry condition, right? So that's still to be true. This had to be 0, so this is 0, yes. The new thing, the thing that we're going to do now is that we're going to identify in this expression here all the pieces that cancel on the equations of motion. So we're going to rewrite this as a term which has the equations of motion, and therefore on the equations of motion is going to vanish, and the rest is going to give us another condition, which is going to be interesting, okay? All right, now, in order to do that, so this is d0, and this is the integral over t from t1 to t2. Now I'm going to use this relation that we found, this relation right here. This, I'm going to use it here, okay? And so that means that I have the integral dt, and then I have derivative of L with respect to q. That's the first term, this first term, and this is going to be multiplied by delta q. This is clear. So this term is this term with the delta q and everything. And now I use that the delta q dot has a derivative with respect to time, on the delta q, right? Right? This term. So that means that I can write here plus derivative of L with respect to q dot. That's exactly the same thing. And now the first term, derivative with respect to t, right? Like this. So that now this term is, in part, is here, given by this term. Okay? But I still have the other one. So now I have to worry about the other term. Okay. So let's go for the other term. The other term is minus derivative of L with respect to q dot. That's also this. But now I put the q dot in here. And this is multiplied by the derivative with respect to time of delta t. Okay, so this is this guy. And it also comes from here. Okay? Right? It's the second term. This second term is multiplied by dl dq, is dl dq dot, is dl dq dot times q dot, this q dot times the derivative with respect to time of delta t. Yeah, right? So that's what it is. Now, let's take this out. Okay? Now, what else? I also have this other term, right? So this other term, I'm also going to put it here, okay? And so this is minus L. Minus and minus gives me plus L d dt delta t. Yeah, so this is true. So I already have all these terms already under control, okay? All right. Now, what else? Okay, so let me just see. Now we have dl dt delta t, so I have to add this guy, dl dt delta t, and I have the derivative with respect to t of delta g. All right, and now I close the parentheses. Okay, so this and this is this and this. So that part is easy. Okay, so all I did so far is expressing delta q dot with these two terms. One goes here and the other goes there. Agreed?
Yes.
Yes.
All right. Now I'm going to integrate by parts. So 0. So we are still computing this complicated 0. Huh? So 0 equals the integral over t from t1 to t2. The first term, I'm not going to touch. So this is going to be derivative of L with respect to Q. And this is the one that I integrate by parts, okay? Integrate by parts. So that means minus derivative with respect to T of the derivative of L with respect to Q dot. Okay? All this, I need a parenthesis. Let me just write it like this. And then I can put the parenthesis here, delta Q. So that is integration by parts. There's still a total derivative with respect to time that I'm going to have to add. Huh? I'm going to add it, later on. Okay, so that's one term. Plus, now I also have the integral dt from t1 to t2. Now I have this second term, okay? And here I also integrate by parts, okay? So that means that I have first the derivative of L with respect to t. This is this guy. And now the integration by parts, which gives me plus derivative with respect to t of this whole parenthesis, okay? Derivative of L with respect to q dot times q dot minus L, okay? All right. And now it comes all the terms that I have to put because I integrated by parts, which is the integral dt from t1 to t2, okay? And this is going to be derivative with respect to t of, okay? First term is here I integrated by parts, so that's the piece that I have to add. dq dot delta q, okay? So this plus this has to give me the piece that I had here, and it does, all right? Okay, minus. Here I also integrated by parts. This ddt here, I acted, on the left-hand side, integration by parts. So that means that I have to add, okay, the derivative with respect to time of the whole parenthesis, all right, which is dl, let me just write dl dq dot times q dot minus L. So the whole parenthesis, as you see here, times delta t, right? This delta t. And I can add freely the delta g because this was already a total derivative, delta g. Okay, so I claim that the above expression can be written, like this after I integrate by parts. I integrate by parts this ddt and this ddt here. Okay, you guys agree? Or you guys are already lost?
I'm a bit lost.
I could not hear.
I'm a bit lost on the last part.
Okay, so let's go back here. All right, so let's go back. Let me just look at this term in yellow. Do you see this thing in yellow?
Yeah.
Okay, look at this thing in yellow and this thing in yellow. I claim that the first term in yellow equals the sum of the two terms in yellow afterwards by integration by parts. Well, let us see. Okay, the second term is the derivative with respect to time of the product of the two, right? The product of the two. So that means that it has the derivative of L with respect to Q dot, derivative with respect to time, whole thing times delta Q, but this is going to cancel against the first yellow term, this one. And then there will be another term, which is dl dq dot times the derivative with respect to time of delta Q, but that's what I had here. You see?
Yes.
Okay, and the same for this one. This one equals this one plus this one. Okay, who else is lost? Has a question or wants to comment on something?
I have one question.
Yeah.
I think on the second integral in the last equation,
This.
Yeah, it should be also delta t at the end, I think.
Absolutely. Absolutely. Yes, thank you. Very good. So let me erase this thing here and put a delta t plus. Yes, thanks. Any other comment? No other comment? Okay, so let's write down this whole thing again, okay? So that is 0 equals, okay? Integral dt from t1 to t2 of the derivative of L respect to Q minus the derivative respect to t, derivative of L respect to Q dot. This multiplied by delta Q plus integral dt from t1 to t2 of derivative of L respect to t, partial, plus total derivative respect to t of the derivative of L respect to q dot times q dot minus L. Now this times delta t and plus integral dt from t1 to t2 of the total derivative with respect to t of a bunch of terms, dl over dq dot delta q. Here is a dot, minus derivative of L with respect to q, q dot minus L delta t plus delta g. Okay, so this is the whole thing. All right. Oof. So that was painful, huh? Now, you can already see that there are terms like, for instance, this one that I'm signaling now, this one, which is going to vanish on the equations of motion. So part of the work has been already done. Okay, this is going to vanish. But we still have to work some more. And in particular, we have to work, this second term here. So this is what we're going to do next. But it's already, almost 2 hours. And I can understand that you guys must be tired. So I'm going to leave now as an exercise, and I'll do it the next day, yeah? Now we have to work out derivative of L respect to t plus the total derivative respect to time, derivative of L respect to q dot. Here there is a q dot minus L equals, now we have to compute this. We have to compute this, inject it in here and look at the consequences. And this is what I'll do the next day. All right. So let's see whether you guys, let's try to do this thing. You have to remember what depends on what. L depends on q dot. So when you take the total derivative, you have to be consistent with all the derivatives. Let's see whether you get the right expression. I repeat that I'll do it the next day, but I'm going to leave it as a little exercise for you to practice, okay? Okay, so any question or comment? Otherwise, I'm going to leave it at this point. Any other question or comment? All right, good. So then let's stop at this point and we'll take it from here the next day. All right, so thank you very much.